Hello there, this is more Least Squares Regression Line. We saw a little bit of this in exercise 5C.1. Now, in that, we basically found out how to find the Least Squares Regression Line, and there were two versions of it. You basically either use the calculator buttons. I was tending to use the Casio Class Whiz, but you can do it on other calculators as well quite easily. And the second method was to use a set of formulae. Now, I want to do two things in this. I want to look at formulae. I want to look at coded data. Actually, there's a little bit in between as well. But before we can get onto that, I suppose there's an element of me that says just make sure you can do these questions. So this is based on what we saw on exercise 5C.2, I think it was, where we got given some formulae. And if you remember, you had three formulae to find. First of all, R was equal to, B was equal to SXY divided by SXX. Now that kind of implies that we know what these things are. And SXY was sigma XY minus sigma X, sigma Y over N. And the SXX was a very similar formula, as much as it was sigma X squared minus sigma X. And you have to square that. And also divide by n. And these formulae therefore work out what b is. And b, you might remember, is the gradient. We also needed the a. Now, to get the a for our equation, you use the fact that we knew it went through the mean point. So we use y minus y bar equals b, which we just found, x minus x bar. So you have to find the mean values as well. And the last thing I suppose you need to do is just remember, make sure you write it in the form of y equals a plus bx. So this is the standard way of writing it, which is akin to y equals mx plus c, I suppose. It's just a line of best fit in a straight line equation. So what I want you to do is two things. First of all, use these formulae, and then comment on the accuracy of your results. And I'm going to pause the video now, and what I want you to do, I suppose, is to have a look at this and use what we saw in exercise 7C.1 to find these, and then we'll talk about these things in a bit. Okay, good luck. Okay, welcome back. Look, so what did I get? First of all, I want to show you my answers for the first part, and there they are. So we got y equals 75.0 minus 0.72x. So this is what you should have got for your b value, I suppose. And this is your a, which you get on. We're chucking into the other formula. Now, I suppose that's the line, but B then says this regression line is used to estimate the percentage sand content at two different depths. So at 25 and 100. Now, we're basically quite common to see this, where you're basically asked which of these is the right one to use. Is it okay to use it on 25? Is it okay to use it on 100? And you should by now have sussed that at 0 centimeters to 48. This was the range of data that we used to find these values. So anywhere between 0 and 48. If we've got a straight line, then it's reasonable to assume that anywhere between 0 and 48 will give us a good approximation, I suppose. And so straight away, 25 you realize is good, 100 is bad, because 100 is not in the correct zone. The other thing to note is it gives us a correlation statistic. Now you can kind of ignore the fact that it's minus. It's a 0.9. That means it's really close to, well, in this case, -1. And basically it means that we've got a set of numbers and they are in a really good straight line. Now, admittedly, they're going down, but they're really tightly packed along that line because of this value here, minus 0.926. So I would conclude that this tells me they're really close to the line. The 25 is within the 0 to 48 interval. Therefore, that will be a good approximation, but the 100 less so, because we're not really sure what goes on beyond 48. So what did I write? R close to 1, so points close to the line. 25 is within the range, so reliable. 100 is outside the range, so unreliable. So there you go. I hope that makes sense. So let's go on to the new stuff. Now, first of all, we've got this alternative formula, B equals. Now, I think we saw this before, but maybe not. So I'll just go through it again. This is a formula sometimes given to you instead of the one like we just used. And the great thing about this is this top thing, actually it's got a name, it's called the covariance. But this SXY is equal to this formula as well. So if they give us this, we don't have to do any calculations at all. SXX, likewise, if they give us this one, this is equal to this is equal to this. So in this example here, it says if sigma x is this, blah, 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 it gives me all this data. Find the equation of the least squares regression line. And all I need to do is go, well, straight away, this thing here, I know is SXY is 240. And I also know, from this, I know that SXX is 70. So really, if they do this in the exam, suddenly I can find B very easily. It's 240 divided by 70. And I'll just do that on my calculator now. Bear with me, got to turn it on. Okay, and I get 3.4 and a bit, 3.43 I'm going to say. And of course now I just need to find my x bar, which is 52 over 7, which is 7.4 and a bit. And I need my y bar, which is, where's my y bar? 108 over 7. And what's 108 over 7? 15.43. So this one's 15.43. So therefore I get my equation y minus y bar equals my b times by my x minus x bar. And presumably I can just multiply this out. And that gives me, obviously, the y minus 15.43 equals 3.43x minus, I just did it on my calculator, for 25.49. Now, obviously I can move that over and I get y equals, now if I do it in the correct order, that becomes a plus, that's a minus, and it gives me 10.0 plus the 3.43x. There it is. So I want a brief discussion about controlled variables now, and different types of variables. So controlled variables is where I mean, look, I've deliberately drawn this little physics experiment type thing going on over here, because very often in science you are able to control one of the variables. It might be the angle at which you do something. It might be the mass you put on the end of a spring. And then you're looking at what happens as a result. That's called a controlled response scenario, I suppose. And the variables are, notice the position of the controlled variable is always on the x-axis. The response is always on the y-axis. Now, we sometimes get what would be described independent and dependent variables. And I want to talk about these as well. Now, independent, if you get one independent variable, it always goes on the x-axis, and the dependent goes on the y. That's a bit like this. The response of the spring, if you like, will change according to the mass you put on the end of the spring. The response dependent, you can see the kind of one depends on the other thing. If you get two independent variables, you can theoretically put them up either way round. And I'll give you an example of these three types of scenarios then. So my first one, my controlled response, I've already given you an example about putting the mass on the end of a spring. I thought of one, you roll a car down a slope. Now you might put different types of friction, and you might know the level of friction, you might know the coefficient of friction for the slope, and you measure the time it takes for the car to reach the bottom of the slope based on that. And so you can control the level of friction on the slope, and the time it takes to get to the bottom is your response. One's controlled, one's response. A geography experiment, I thought here about, look, you measure how much rain falls on a plant. And you might do this in several different locations, and dependent on where you are, you've got different amounts of rain. Now, the amount of rain you can't control. There's no way you can control how much rain falls. So that's independent. It's not controlled, it's independent, but it goes on the x-axis. What is dependent on that is how much the plant grows, how much crops are produced. That's the kind of scenario I'm thinking of here. An example of the last one, I'd call this a maths experiment. I'm not sure if that's a good example, but it's the kind of thing we do in maths, at least on paper. We weigh a lot of students. We also measure the height. Now, look, there's no way I can control how tall somebody is or how heavy they are. It's just a random set of sample. So both are independent of each other, but there may still be a link between these two things. So just be aware of these three examples. Now, the last thing I want to do with you is what I call coding. And coding is probably a good way of describing it. You might also call it a transformation. It's where, for instance, I've got an example here that you're going along and you've got a formula, or a least squares regression line for miles per hour, but you want it in some other, it might be kilometers per hour or meters per second, or you might change from Celsius to degrees. And this is what this is here. So bear with me, I've got this example. Now I've got my equation for number of ice creams sold. Now y is the number of ice creams sold. And my logic is x is the temperature on the day. And my logic would be that the higher the temperature, the more ice creams I sell. And I've got this equation that says y equals 21.6 plus 6.3x. But look, x is the temperature in degrees C, and if I want to change it into Fahrenheit instead, now Fahrenheit's an old measure, but they still use it loads in loads of countries, including America, so it wouldn't be unusual to have to do this. But this is just becomes an algebraic trick, really. So f equals this, but of course this says x, so we just rearrange that. F minus the 32 will equal 1.8, and therefore f minus the 32 over the 1.8, I've missed out my x there, that was bad. F minus 32 over the 1.8 equals the x. Now I've got x equals, I can sub into here. So I've got y equals 21.6 plus 6.3, and rather than x, I can now write f minus 32 divided by 1.8. What's that give me? Y equals 21.6. plus, now 6.3 has to be divided by 1.8. That's probably the easiest way of doing it. And I get 3.5. If I divide that by that, so now I can multiply out the bracket. Y equals 21.6 plus 3.5 f. I've got to do 32. Just turn my calculator on again. I've got to do 3.5 times that 32. I get 112. So that's minus 112. So y now is, well, I've got to do 21.6 minus 112. That's minus 90.4. Plus 3.5f. So let's see if that's right. Yeah, minus 90.4 plus 3.5f. Now, there's another question, actually, and it refers to the fact, it says it is also known that the correlation between the variables is r equals 0.65. And I suppose what it wants us to do, find a new value of the correlation coefficient after we've made this transformation, after we've coded the data. And so we've got this set of points going up into some kind of straight line. I'm not exactly sure what they look like. I made it up. But we had x across here, and there's y. And I suppose the question is, what happens to the scatter graph if you change the one of the variables? And in this case, I've got f has replaced the x. The y stayed the same. And the answer is not a lot. So my answer is still 0.65. There's no change whatsoever to the correlation. Basically, the points are still in the same place relative to each other. They might be slightly stretched or something, but they're still in the same place. Now, I've got one more example of this. This was where you did two transformations. So it says y equals 4x plus 2. That's my initial line. That's my least squares regression line. But then I do one transformation to the y-axis. And I don't like the way it says p equals 2y, so I'm going to change that to y equals p over 2. And I've got this other one. Again, I don't like the fact that it says q equals. I would prefer it if it said x equals. So x equals q plus 1. So I'll get my two transformations, my two piece of coding, and I rewrite this. Y is now p over 2 equals 4 lots of q plus 1 plus 2. That's 4q plus 6, I reckon. And I multiply that out. But that's p over 2. So I reckon p equals 8q plus 12. Let's see if that's right. 8q plus 12 is right. So it becomes quite easy once you realize all it is a piece of algebra. So it starts off to be a statistical question, and in the end it's just algebra. Look, so that's all the questions I've got for you on this. We're going to do 5C in class, or if you're at home doing this, then you've got the book, then enjoy that as well. But that should be a good overview of the additional aspects, the complications, if you like, the extra questions you get on exam questions on linear regression. It's not just about finding the equation. Very often you get some other bits like coding, like talking about the types of variables you have, and